I also think of time as this prison. Time makes us all a prisoner of the present, forever transitioning from our own past into an unknown future. We can move back and forth in any other coordinate, up and down, left and right, forward and back, but we're stuck in time. We can't move forward or backwards in time arbitrarily. So that coordinate has a kind of a fundamental difference from the other three. The earliest astronomers basically invented timekeeping, all right?
Yeah.
So all measures of time historically were derived from cosmic rhythms. So today we would say the rotation of the Earth, but in the day it was the movement of the sun. So that gave you a day, and then the sun's position on the sky throughout the days differed, and temperatures changed, so that gave us the seasons. And then, of course, back then it was the sun doing all this, but we would learn that we rotate and we revolve around the sun. So that took really long to figure out, disturbingly long. I mean, only like 400 years ago. So what it tells you is that you can keep track of time even though you have no freaking idea what's going on. Because all that matters to you is that things repeat. If you have something that repeats predictably, you have created a timekeeping mechanism where the faster you move, right, the slower time ticks for you as others view it.
Relative to the observer.
Relative to the observer, correct. You don't know anything's happening.
Right.
Your clock still ticks as far, you still got your heartbeat, all of this, okay? So this is not a physiological thing. It is an actual property of the fabric of space and time under those conditions. So I watch you fly by, and the faster you go, the slower time ticks for you, okay?
But my time stays the same.
To you.
To me. Right.
To you. So not only does speed do this, also the strength of a gravitational field will have the same effect on you. The stronger the gravitational field is, the slower time ticks for you. While we're there, let me just slip this in. The GPS satellites orbit higher than like the space station and other things that are in what we call low Earth orbit.
Low Earth orbit.
So the geosynchronous satellites are like middle orbit. That is far enough away from Earth's source of gravity for them to have a measurably different space-time condition.
Oh.
So that their clocks tick faster than our clocks on Earth's surface, because they're farther away. And so, remember I said the more intense the gravitation, the slower time ticks. So they're farther away, their time ticks faster relative to us.
Wow.
But we get precise timings from geosynchronous satellites. So how does this work? We pre-correct the time signal from the GPS satellites to compensate for Einstein's general theory of relativity, so that by the time the time reaches us, well, it's been properly corrected and it matters to us and our space-time continuum, not the one that's at middle Earth orbit. This is real, okay? This is the real universe we're talking about here. Okay, so now watch. Let's keep going faster and faster. Let's go half the speed of light, 3/4 the speed, 90% the speed of light, 99% the speed of light.
Mm-hmm.
Time is ticking slower and slower and slower. For you will watch the whole future history of the universe unfold in front of your eyes as fractions of a second go by for you. As you go 99, there's a formula for this, of course, but 99, 99.9, 99.99% the speed of light.
Because you're the observer of that. Your time has slowed to the point where as you observe the things that are not moving at the speed of light, you see them
speeding up. Correct.
You see
speeding
them
up.
Unfold.
Correct.
Boom. God.
Correct.
That is insane.
Okay. So now watch.
Oh my God. Wait.
No, watch. Okay. There are particles that decay. You've heard of like radioactivity, right?
Yes. Right.
It's one part, it decays and becomes another part, and it releases often deadly energy.
Yes.
Okay. Radioactivity. All right. Some particles, let's take, for example, the proton decays in like 6 minutes when it's left out in the wild. Okay. When it's not part of an atom.
Okay.
When it's not in captivity, I forgot which of these, but it doesn't matter for my example. Decays in like 6 minutes, okay? Okay. What happens if you take that particle and speed it up in a particle accelerator? So you take a community of these particles, speed them up, calculate, wait a minute, the internal wristwatch on these clocks says they should live longer. And sure enough, their decay time takes longer.
Wow. That's, oh my God.
Yes, yes.
Oh, wow.
Yes.
And that becomes living proof of what Einstein said.
Yes, because we can't go half the speed of light.
Right.
So you can accelerate a particle to do that.
Yes.
It's an internal built-in clock that decays after a certain amount of time, and there they are taking longer to decay in the exact amount that Einstein predicts. Now, let's take this to an extreme level.
Right.
Let's go so fast that we're going the speed of light itself.
Right.
Well, we can't do that because we're made of material substance, and there's no way to do that. But there are things that travel at the speed of light. And what is that? What travels at the speed of light? Light does. So if photons had a clock, the clock would never tick.
Nice.
Which means when I go to a mountaintop, as I did in graduate school, to observe the center of the Milky Way galaxy for stars that emitted their light 30,000 years ago, traveling through the gaps of interstellar space, and they move through space, come through Earth's atmosphere, they come down into the telescope, they reflect, go back to my detector, and land on my CCD chip. That photon, when it was born, at the star that emitted it, was detected at my telescope in the same instant.
Wow.
According to the photon itself. The photon has no knowledge of that trip.
Right.
Because time did not exist for it. And some photons go right on by Earth and are still moving, but they have no internal time clock. And so just the idea that light can move across the universe and have no, and not age, this is a fascinating fact to me.
Wow.
So, yeah.
That is more than fascinating.
Yeah.
I mean, that's mind-boggling.
Yeah. So that is light, the age of light. It's like it doesn't age at all.